So this is where we officially start talking about functions. And functions are a very big deal in pretty much every area of mathematics. If you study trigonometry, you spend a lot of time dealing with trigonometric functions like sine and cosine. If you study calculus, you pretty much spend all your time doing calculus kinds of things to functions. If you work with a halfway advanced calculator or a spreadsheet program, it's got lots of built-in functions that will take a number or maybe a set of numbers and perform some calculation on them and give you the result. So today we're going to talk about what functions are, the basic idea behind what a function is and some of the basic ideas involved. And then in upcoming sections, we'll be learning more about functions and what we can say about them, just functions in general, and then on to talk about specific kinds of functions. And one way of thinking about what a function is that it's a kind of relationship between two different things, two different variables, where one of those things depends on or is determined by the other. So if the value of one thing depends on the value of something else, we can say the one thing is a function of the something else. So for example, the cost to mail a package might be a function of the weight of the package. So if you've got a package to be mailed, you take it in, they weigh it, and then based on how much it weighs, they tell you how much it's going to cost to mail the package. If you have a ball and you drop it or throw it up in the air or hit it with a baseball bat or something like that, over time it's going to go up or come down, and its height above the ground, you can think of that as a function of time. Here's how high it is after 1 second, after 2 seconds, after 3 seconds. The proper dosage of medicine might be a function of a person's body weight. The area of a circle is a function of the radius of the circle. Maybe you're familiar with the formula area equals pi r squared. So you can plug in a number for r, the radius, and that will tell you the area of the circle. The temperature in degrees Fahrenheit, you can think of that as a function of the temperature in degrees Celsius. There's a formula that you can use where you can plug in the temperature in Celsius and get out what the temperature would be in Fahrenheit. And if you work at a job where you get paid by the hour, then the amount you get paid, the amount of money you make, is going to be a function of the number of hours you work. That's what determines how much money shows up on your paycheck. So here's one specific example. Suppose the rent for an apartment is changing from year to year. So in 2017, it was $800 a month. In 2018, it was $950. In 2019, it was $1,100, and so on. So you can think of the rent as a function of the year. And there are different ways we can specify that relationship. I could give you a table of values for each year. What's the rent in that year? Or I could think of that as a set of pairs of numbers, where the first number in each pair is the year, and the second number in that pair is the rent for that year. So if you just think of that as a set of ordered pairs, ordered because it matters which one's first and which one's second. The way I've got it set up, the first number in each pair is the year, and the second number is the rent. You can also formulate that as an equation or a formula where you have a variable standing for the year, and then the formula tells you what calculation to do with that year number to get the rent for that year. So with this particular set of numbers, if we take 150 times the year, 17 or 18 or whatever, and subtract 1750, we get the number that goes with it for the rent. And we can show it as a graph where the points on the graph have coordinates that correspond to those pairs of numbers. Now here's another possibility for rent as a function of the year. In this example, the rent was $800 in 2017. It was still $800 in 2018, but then the landlord raised the rent and took it up to $1,100 in 2019, and then it stayed at that level for 2020 and 2021. So that still counts as a function. It's no longer a straight line, but it's a function. You tell me the year, I can tell you the rent for that year. And again, we can think of it as a set of ordered pairs, or as a set of points on a graph. Here's another possibility. There's no clear pattern here, but I can list the rent for each year from 2017 through 2021. And so that gives you what the rent is as a function of the year. Now here's an example that's not a function. This does not give us rent as a function of the year. Can you see why not? It's because of these two pairs of numbers here. The first one that says that in the year 2018, the rent was $500, but then it also says that in 2018, the rent was $700. So if the rent can be more than one thing for the same year, then the rent doesn't depend on just the year. Now, it might be that there's two different apartments that have different rents, but in that case, the rent depends on which apartment we're talking about and not just on what year we're looking at. So for rent to be a function of the year, then there's got to be a relationship where for each year, there's just one rent for that year. That means you can't have two different pairs of numbers with the same first coordinate. On the graph, that would mean that you can't have 2 points with the same, like, x coordinate, which puts them at on the same vertical line, just one directly above another. So if we have any set of ordered pairs, that would be a relation. You can still say there's a relation between the two variables, but for it to be a function, no two ordered pairs can have the same first coordinates. So look at these examples. In this example, we have a set of 5 ordered pairs, 0, 3, 9, 6, 4, 3, 7, 7, and 3, -1. For that to count as a function, we cannot have any two of those pairs with the same first coordinates. So is that a function? Yes, it is. What about this second example? Is this a function? Well, notice we do have two pairs that both start with the number 2, but then they have different second coordinates that go with that. So that means that, no, that's not a function. Now, what if we have an equation that relates x and y? Anytime I write down an equation with an x and a y in it, I can think of that as a relation between x and y, and then you have a bunch of pairs of numbers that satisfy that equation. But for it to be a function, each x has to go with only one y. So for any particular number you put in for x, there's got to be one specific y that goes with it in order for that equation to define y as a function of x. So in these examples, that's the question. Does each of these equations define y as a function of x? Well, for the first one, the answer is yes. It says y equals 5x cubed minus 13. So that's telling you exactly what you have to do to x to come up with the y that goes with that x. You have whatever number x is, you have to take 5 times that number cubed minus 13 to get y. So if I come along and put in the same x that you put in, I'm going to get the same y that you got. So that is a function. So if your equation is solved for y, if you have y on one side equal to, and then you've got a rule telling you what to do with x, that's a function. What about the second equation? The way it's written now, x squared plus y equals 4, is not solved for y, but I can rearrange it. I can get it solved for y just by subtracting x squared on both sides. So there, y equals 4 minus x squared. So yes, that does define y as a function of x. Whatever number x is, y is going to be 4 minus that number squared. But what about the third equation, x plus y squared equals 4? If we try to solve that for y, well, I can subtract x on both sides and get y squared equals 4 minus x. But if y squared is something, then y could be either the positive or the negative square root of that thing. There's more than one possibility. Like, for example, if x is 0, y could be 2, or y could be negative 2. 0 plus 2 squared would equal 4. 0 plus negative 2 squared would also equal 4. There's more than one y that goes with the same x, so it's not a function. That one does not define y as a function of x. So, to recap, for an equation to define y as a function of x, you've got to be able to solve it for y, so it gives y as just one specific thing for each x that goes in. Now here's what we have left to talk about in this section. We have to talk about domain and range, what those mean for functions and how to find them. And we'll talk about how function notation works when you're actually evaluating a function based on its formula. So I'm going to end this video here and come back in the next video and we'll talk about those things.